Hello and welcome to part 2 of our studies of K-means clustering. So here is my assumption as we get into this. I assume that you have already been through the first part of our lecture on K-means clustering and unsupervised learning, and you've also learned how to create a baseline K-means clustering model that simply has a starting point for the total number of clusters, and that is where we have stopped, right? So when we stopped in the previous video, we just set a number of clusters of 3, and we left it off saying that there is a better way or an optimal way to figure out how many clusters you should create when you do use K-means clustering with unsupervised learning. So if that is not the case, go back and check those videos out. So what I am going to assume is that you've got our NFL data and it is already loaded up into the original 5 clusters that we started with. And I want to jump forward to talk to you about how the K-means clustering algorithm really works. So we're going to skip through some of the stuff that we did in the previous videos. And what I want to land on is this right here. So what I want to talk to you about is how the K-means algorithm actually works, right? How do we actually get observations into clusters? How does that process work? So remember when we use the K-means algorithm, we have to set a random state. Well, we set that random state because when you first start this process, the iterative process of clustering your data together, it's going to put observations just randomly in the clusters that you've created. So if you have a number of clusters of 3, you're going to have 3 clusters and all of your observations are going to be randomly assigned. So what's going to happen from there is the algorithm is going to start calculating the distance between the centroid, which is the center of that cluster, and all the observations that are randomly in it. Once it does that, it's going to calculate the sum of squares error. So basically the difference between the center and all of the other options, all of the other observations inside that centroid. Inside that cluster. And the goal of this process would be to minimize that sum of square error. So what will happen is the clusters will start switching observations in and out. Basically, they'll slowly start moving around, and the number of observations inside each one of those clusters will slowly move around with the purpose of reducing that sum of squares error. And when it gets to the point where the sum of square error does not get any better if you move an observation between clusters, we call that process convergence. So now that's a lot to think about. So let me go back a step and show you. So here is an example of 3 clusters. The stars that you see, 1, 2, 3, those are the center points of each one of those clusters. And if you're using the data set that I gave you, each one of these data points that you see, those are the different quarterbacks in our data set. So when you first start the process of creating these unsupervised clusters, the quarterbacks are just going to randomly be assigned to one of these 3 clusters. Okay. And what's going to happen is it's going to start calculating the distance between the center and observation, and the center and observation, and the center and observation. And it's going to calculate the sum of square error, right? The difference between where that observation is and the cluster. So that distance observation that you're looking at, right, or that distance calculation, saying the difference between these points on average, like so the total average, the goal of that would be to be as small as possible, because that means they're the most similar. Right? So slowly what's going to happen is it's going to start swapping these observations around. So think of it like the cluster slowly sort of moving. And when it gets to the point where the sum of square error doesn't change anymore, it stays the same if the observation moves, or it gets worse. We call that process convergence. And at that point, this model is done. Okay. So that's how it works under the hood. And remember, it uses Euclidean distance to calculate the distance between the center point of each cluster, so center point, and the observations inside that cluster. When in doubt, also remember in your book, pages 377 to 399, talk about all the things that we just talked about. What I want to spend the rest of our time together today doing is showing you how to figure out the number of clusters to use. So when we got started, we decided that we would use 5 clusters because on our football team, we have 5 strings of quarterbacks. That's probably not the best way to figure out how many clusters to use. So if you are following along in the data mining book, if you check out page 399, it's going to talk to you about different methodology that you can use in order to figure out the optimal number of clusters for your data set. I'm going to show you one of those methods now. Okay. So I'm going to jump out of this and I'm going to go back into Colab. And I need to reconnect to Colab like so. and I need to run everything to get caught up. So let's do that. So I'm going to quickly rerun everything. Okay, there we go. So what we've done so far is a quick refresher is we've gone through and we've decided that we're going to use touchdowns, yards, and interceptions within all of this data of quarterbacks to break the quarterbacks into tiers. So first tier quarterbacks, second tier quarterbacks, so on and so forth. Okay, so we're going to break them into clusters based on similar characteristics, touchdowns, yards, and interceptions. Okay, so now because the K-means clustering algorithm uses Euclidean distance to calculate, we had to go through and normalize this data. So we used the standard scaler to rescale all the data on a value between 0 and 1. We instantiated our model. So basically we created our model and we started off with a baseline of 5 clusters, understanding that there's probably a better way to do this, but we just picked a number to start with because we have 5 strings on our school's quarterback team, or excuse me, on our team's football team. So we just went with that. So we went through, we created our clusters, and this is what we see. Okay, so you've got 5 clusters. Maybe it's okay, maybe it's not. So what we have the ability to do is find a way to optimize the correct number of clusters. And we can do that through creating an elbow plot. So what we're going to do to create this elbow plot is we're going to do something kind of similar to when we found the optimal value of k for k nearest neighbors, but not exactly the same. So what I'm going to do is I'm going to create a list, and it's going to be an empty list with nothing in it. And I'm just going to do SSE for sum of squares error. So just an empty list like so. Okay. So the next thing I'm going to do is I'm going to create a loop. So I'll say for k, which is the number of clusters we're going to use, in the range. And we'll start with something simple. We'll say just like 1 through 40. Okay, so 4K in the range 1 through 40. So now at this point, we're going to recreate our model just like we did when we were just starting with the baseline. So I'm going to create the name KM for K-means. I'm going to use that K-means algorithm. And from there, we need to specify the number of clusters. And instead of me putting in the number 5 here, I'm going to put in K. I can set my random state, which can be really anything you want. And then I'm going to go through that process. So after I've created the model, so I need to go in and fit it. I'm going to fit it to my X norm DF, right? So my data frame of normalized values. And then this is where it gets interesting. So what we need to do is we want to take that error and we want to put the error, the SSE that we're creating, which we're going to call inertia, into something that we can plot. And in this case, we're going to put it into that list. So what I'm going to do is I'm going to append this list that I created. So I'm going to do SSE dot append. And I'm going to append it with the K-means model that we're creating, but I'm going to use this inertia option right here. So we're going to append it with K-means inertia. And outside of that, that is all we need. Uh-oh, did I spell something wrong? Yep, I sure did. So right here where I put a colon, that should be a comma. And there we have it. Okay. So the first thing is, if I look at this, if I just look at the list, I'm going to have a bunch of numbers in it, just like so. Okay. And these kind of don't make sense just yet. But if I were to plot it, I'm going to see something interesting. Interesting. So I see a plot. Okay. So here's what you're seeing. Going up in this direction here, this is your error. And then here are your number of clusters that you're seeing down here, right? So there's your clusters, 0 through 35, or 0 through 40. And then up here, this is your error. Okay. So remember what the error is telling you. It's the total error of the distances between the centroid and all of the observations inside the centroid. So if I were to have just 1 or even 2 clusters here, so 1 or 2 clusters, something like that. So if I had, say, 0 or 1, I go way, way, way up here. That's going to be a pretty big error. Okay. But if I have 35, that's going to be a pretty small error. But that's because pretty much every quarterback in our data set is within its own cluster. So that's not very helpful, right? So if you have 1 cluster for every person, the error is going to be very small, but that's also not useful if you have a 1-to-1 ratio between observations and clusters. So the sweet spot here between looking at the sum of squares error or the distance, the average distance between the centroid and all the observations, and looking at the total number of clusters that are happening inside this data set, the sweet spot happens right in here, where the bend of this plot is. So we could call this 3, maybe even 4, more like 3, and right in here. So instead of having 5 clusters, if we have 3 clusters, we're going to hit the sweet spot between the total number of clusters and that sum of square error, right? Because it's going to be way down. Notice if you only have 1 cluster, the error is way up here. That's because all of the observations are inside 1 cluster, so therefore the distance is going to be huge between the center of that point and everything else, right? But look at how quickly it drops, and look at where that sweet spot hits before you start getting into the 1-to-1 ratio situation, okay? So what would you do with this? How would you use it? So you'd look for the bend in this plot and find kind of your sweet spot. And then you would go back and you would simply remake the cluster model with 3 instead of 5. So I could jump back up here and I can take this and take it to 3. And I'll just start rerunning everything. And 0, 1, 2, so we'll take these away. And we'll take these away. And now when we look at it, we have a much more optimized version of our clusters. So right up here, we had our 2 standout quarterbacks for the year, right? So we had Drew Brees and Peyton Manning. If you looked at it before, you had Drew Brees and Peyton Manning in their own little cluster, which doesn't really help you have a cluster of 2. So now when I look at it, here's our lower tier quarterbacks, here's our mid tier, and here's our top tier. All of a sudden, this is really clearly defined and it's much easier to use. So that's just a technique that you can use to find the optimal number of clusters when using K-means clustering for unsupervised learning. This is called the elbow plot method. If you are using the data mining book that we are using in class, check out page 396 to 399. It'll talk to you about that a little bit. Outside of that, look forward to seeing you guys soon, and we'll be back with another one any day now.